Hi guys, welcome back. So today we are gonna continue to simplify radicals. There are gonna be times where we will have to use the product rule for radicals to simplify the expression, and there will be times where we will have to use the quotient rule to simplify the expression. So let's go ahead and break it down. So the product rule for radicals says this. I'm just gonna write it over, okay? And I will explain with an example. Okay, so the product rule for radical says this: if we have the nth root of a product, if need be, we can split the factors. How? We're going to say nth root of the first factor, operation between these two is times, so times nth root of the second factor. Remind me next time just to write it out. Okay, am I gonna have space to show the example? I don't know. Okay, nth root of a times b. If you have a multiplication problem, you can split it. How? It's gonna be nth root of the first factor. Remember, the operation is times, so multiplied by the nth root of the second factor. This is going to be a very important property when we start to simplify these radicals. Now, what if you are taking the nth root of a fraction? So if you have the nth root of a fraction, or in semi-English, what if your radicand is a fraction? If your radicand is a fraction, then in this case you're going to use the quotient rule to simplify the radical. How? We're going to take the nth root of the numerator. I'm just going to write down the answer. Nth root of the numerator over nth root of the denominator. Okay? And I think I'll illustrate when we get to the actual examples. Something to keep in mind when you come across simplifying the radicals is just how to go from radical form to exponential form. Okay, if we have the nth root of b, we have the nth root of b to the m, how can I write it without the radical, or my fancy math words, how can I write it in exponential form? So to do that, you're going to keep the base, which is b, and then write the exponent as a fraction. How? It's going to be current exponent divided by the index. So if you want to remember formula wise, nth root of b to the m equals b to the m over n, be my guest. But you know what? It's just so much easier if you remember it in words, okay? Or remember the process. The only way we can have these things in the back of our mind is if we have plenty of practice, and today will be one of those days. I think I have like 10 problems for you. Oh, I don't know how to count, A through M, whatever that is. Okay, now one of the questions that I get is this: how can I tell when the radical is simplified? Okay, so there are 4 things that need to have been met in order to make sure that our radical is simplified. So let's do this. The first thing is the radical is simplified when the radicand has no factor raised to a power greater than or equal to the index. Yeah, let's pretend like we understood that. Okay, so let's go ahead and do an example. So I want to know, where am I? So we have cube root of x to the 11th. Okay, so pretend I read that already. So how can I tell if my radical is simplified? Well, check it out. If we have exponents inside, we have to make sure that the exponent is less than the index. Okay, if it equals the index or higher, that means we can tone it down. So let's go ahead and simplify it, because we're overachievers. Okay, so I'm like, oh man, I lost my train of thought. So I'm like, oh man, 11 is not under 3, so I can simplify it. So how are we going to do that? We're going to go ahead and write it in exponential form, or in English, get it out of the radical. So to do that, we're going to keep the base, namely x, and then write the exponent as a fraction. Okay, it's going to be current exponent divided by the index. I tend not to write the fraction bar by using a diagonal, but I ran out of space. Okay, and then at this point we're just gonna divide, and I want you to give me old school answers, meaning highlight the quotient and remainder. Don't like get all excited and write it like in decimal form. Okay, so I know that you know that 3 goes into 11. I don't know, sorry, I'm a little nervous. Okay, so I know that you know that 3 goes into 11 at most 3 times with the remainder 2. So let me go ahead and write that. Okay, so we want to highlight the quotient and then the remainder. Okay, like when you were in kindergarten before the decimals came in. So now the question is, how can I tell if I'm going to have a leftover radical? If you have a remainder, well, guess what? You're going to have a leftover radical. So to clean this up, the quotient tells you how many factors come outside. Sorry, though in this case the quotient is 3, so that means that 3 factors of x come outside. The remainder, if any, will tell you how many factors of x will stay inside the radical. The remainder is 2, so that means that we'll have 2 factors of x. So let's go ahead and put the radical. We'll put that x squared, and then if we have a leftover radical, we have to preserve the original index unless we could tone it down by something else. Okay, so we had the index of 3, so we have a leftover radical, so we need to keep that index of 3. Okay, so now I'm like, is this really simplified? Okay, cool. We have an exponent. Is it under the index? Yeah, okay, it's less than the index, so we're good. Now, what are other things to watch out for to ensure that our radical is simplified? So it says exponent in the radicand and the index of the radical have greatest common factor of 1. Okay, too many words. So let me go ahead, write down the problem, and then I'll break it down for you. Okay, so the example will be 4th root of x squared. 4th root of x squared. So I want to ask myself, is this bad boy simplified? I'm like, I don't know. I got an exponent. I got to make sure it's less than the index. And I'm like, okay. So at a first glance, I'm like, yeah, this radical is simplified because 2 is less than the index. Cool. So we cannot simplify in the sense we can take some x's out. But in this case, it's actually the radical is not simplified. Why? Well, it's not simplified because like the exponent and the index have a common factor other than 1. So we need to tone this down. Okay, it's really hard for me to see how we're gonna tone it down. So what we're gonna do, we're gonna write this in what we are going to do is write this in exponential form. So get it out of the radical. So to get it out of the radical, we're going to keep the base of x and then write the exponent as a fraction. So how? Current exponent divided by the index. Current exponent divided by the index. So now when we write the radical in exponential form, it's a little bit easier for me to see like, oh yeah, that's why the radical is not reduced, because we could tone down the 2 and 4. So I know that you know that 2/4 reduces to 1/2. So I'm going to go ahead and write this as x to the 1/2. And I know that you know that whenever we have a rational exponent, or in English, whenever we have a fraction exponent, that is code for hidden radical. Okay, so first we're going to start out with the denominator. The denominator is 2, so that means that the index is going to be 2. Okay, so we're going to have the square root of whatever we're left with. We cover up our denominator and we're left with x to the 1st power. Okay, so we want to tell the world, the 4th root of x squared is just code for square root of x. But let's go ahead, clean this up. When the index is 2, we typically don't write it, so let's not start now. Okay, so we omit it. When the exponent is 1, same speech, we typically don't write it, so let's not start right now. Okay, so from the top, the moral of this story is that the 4th root of x squared can be simplified to square root of x. Fantastic. What is another thing to look out for to determine if the radical is simplified? So let's go ahead, look at number 3. So the statement number 3 reads, the denominator, if any, does not contain a radical. So in this case, let's just go ahead, look at 3 times the square root of 7. Okay, so the question is, how come it's not simplified? Well, that's because that's one of the rules. If we have a denominator, we have to make sure it doesn't contain the radical. Now, right now, we are gonna in today's video, we're gonna focus on using the product rule for radicals to simplify expressions. So we're just gonna table on how to simplify this. This is just something that I wanted to point out. Okay, things to watch out for. If you got a fraction, make sure you don't have a radical in the bottom. If you do, then do what you gotta do to get rid of it. Cool. Things to watch out for to ensure that your radical is positive. So number 4 and the final one reads, the radicand has no fractions. Okay, so something like this. What if I ask you to simplify, well, what if I asked you to simplify some problem and then your answer was cube root of 3/5? So I'm like, well, how come this is not simplified? Well, this goes back to step 3, okay, or number 3. If you got a fraction, make sure you don't have a radical in the denominator. When we use the quotient rule to split the top from the bottom, this will give us cube root of the numerator over cube root of the denominator. When we use the quotient rule to rewrite the radical, it's a little bit easier to see why is it that this bad boy is not simplified. It's not simplified because we had a hidden radical in the denominator. Okay, so I told you the 4 things to look for when it comes to simplifying radicals. 1, we got an exponent inside the radical, make sure it's less than the index. 2, if we got an exponent inside the radical, make sure you can't, bad math, reduce it with the index, okay, like we understand ourselves. 3, if you got a fraction, make sure you don't have a radical in the bottom. 4, if the radicand is a fraction, do what you gotta do so you can see the hidden radical in the bottom and then take care of it. Alright, so let's go ahead and look at fun problem number 1, which are going to be the same directions you're going to see for a while until we get out of this chapter. Okay, so the directions read: simplify each expression. Assume all variables represent positive real numbers. Oh, and I love this. Okay, so I love this disclaimer because if we have a variable, we assume it represents a positive number, so we don't have to worry about tossing in absolute values when needed. Okay, and then when it comes to radicals, sometimes, you know, we have options. You know, we may write them in exponential form, or we may write them in radical form. So we always have to be told in which form to write it. Okay, and if we're not told, then I guess it's a student choice. Okay, but it says write answer in radical form if necessary. So pretty much, if you have a rational exponent, fix it so you backtrack it to radical form. Okay, let's go ahead and knock out problem A. So we have square root of y to the 28th. I'm going to go ahead highlight the index. Okay, so we know it's 2 because we read it as square root. So the question is this simplified? The answer is no. Why not? Because the exponent is bigger than the index. Okay, so we could tone it down. So remember, to simplify radicals, you pretty much have to remember the exponential form. Okay, like how to get out of the radical. If we have nth root of b to the m, to get out of the radical, we're going to keep the base and write the exponent as a fraction. It's going to be current exponent divided by the index. Alright, if you remember this, then we're going to be good. So let's get it out of the radical. We're going to keep the base and write the exponent as a fraction. So to do that, current exponent divided by the index, and then you're just going to simplify that quotient. If it gives you an integer, okay, you know, cool, say thank you or whatever I'm trying to say. If it does, don't like show off your decimal notation, you know, give me old school answers, highlight the quotient and remainder. Okay, but lucky for us, in this case, quotient of 28 and 2 gives us a clean number, namely 14. So we want to tell the world the square root of y to the 28th is just y to the 14th. Cool, one problem down, many more to go. Problem B, where am I? Problem B, yeah, you cannot see that. Sorry. Problem B, we have cube root of x to the 75th power. Cube root of x to the 75th power. Okay, so I don't know what that is, so what am I going to do? I'm going to get out of the radical, or if you want to impress your friends, put it in exponential form. So to do that, let's go ahead and write the following. We're going to keep the base of x and then write the exponent as a fraction. So to do that, it will be current exponent divided by the index. Current exponent is 75 and then the index is 3. Okay, lucky for us, quotient is 75 and 3 is 25, I think. We have no remainder, so unlike like our sample problem, all the factors come out. Okay, so let's go ahead and do, where am I? Problem C. Problem C, we have, we have 8th root of x to the 5th times 8th root of x. Okay, so yeah, that's a little bit spicier, but it is what it is. Okay, so first things first, I'm going to go ahead, make sure that each radical is simplified before we multiply. So index is 8 and this exponent is less than 8, so it's already simplified. Okay, index is 8 and then the exponent, let me highlight it, is less than 8, so I guess it's simplified. So what are we going to do at this point? We have two radicals that have the same index, so we're going to use the product rule for radicals in reverse. Okay, so let me go ahead and zoom out, okay, because I'm running out of space. So I'm going to remind myself, so if we have the nth root of a multiplication problem, we can split it. Okay, how? We're going to write it as nth root of the first factor multiplied. Again, why do we say multiplied? Well, that's because the product between the operation between a and b is multiplication. So if we have the nth root of a multiplication problem, then we can split it. Okay, so it's going to be nth root of the first factor times nth root of the second factor. Okay, but just like we can split it, we can also come under one roof. Okay, we can use the product rule in reverse. So again, we got to make sure that the indexes are the same, and in this case they are. So let's go ahead and multiply the radicands and then house this under one roof. X to the 5th times x. Do what you got to do. If you're having a moment, vent out your frustration. You're like, city exponent rules, they make me so mad. And in this case, if you have a multiplication problem, how are you going to handle it? You're going to keep the base and add the exponents. So the base is x, and the sum of the exponents, namely 5 and 1, is 6. So the product of the radicands will give us x to the 6th, but we want to take the 8th root of that. So it's like, oh, okay, we're on it. So then I'm like, can I simplify this radical? At a first glance, I want to say no, because 6 is less than the index of 8, so there's no x's to come out, like in problem B, per se. So we cannot simplify in the sense of bringing some x's out, but we can tone down these numbers. Why? Because 6 and 8 have some common factors. Do what you got to do. I'm going to go ahead and write this in exponential form, or get it out of the radical. So we're going to keep the base and write the exponent as a fraction. So to do that, will be current exponent divided by the index, and then we reduce and take it from there. 6 and 8 have a common factor of 2, so you can use your cross cancel notation, or like show yourself what you're reducing by, and then we'll tell the world 6 eighths reduces to 3 over 4, or 3/4. So that is the answer. We have simplified it. The reason why this is not accepted for full credit though is because the problem specifically says write your answer in radical form if necessary. Whenever you have a rational exponent or a fraction exponent, that is code for hidden radical. So let's start with the denominator. Since the denominator is 4, then that means that the index is 4. So we're going to have the 4th root of whatever we're left with. 4th root of x to the 3rd power. So I'm going to box this and then say my speech. So I'm like, is the radical simplified? Yeah, because I boxed it, okay? But is it simplified? I don't know. Is the exponent less than the index? It sure is. Does the exponent have a common factor with the index? It does not. Okay, so that's it. We cannot simplify it any further. Cool. Let's do a handful of more problems and then we're out. Okay guys, so our fourth problem has been located, so let's do this. So we are asked to simplify the square root of 48, and it's like, what happened to the variables? I missed the variables, because whenever we had the variables, we would just write it in exponential form. But now the question is, how do we simplify the radical? So first things first, I want to highlight the index. So we're going to read this as square root of 48, and I want to see the index for my peace of mind. Okay, so I'm going to show you two ways to go about it. The first time around, I'm going to assume the numbers come to you, and the second time around, I'm going to assume the numbers don't come to you. You have no idea what I'm talking about, but hopefully after I break this down, you will. Okay, so pretty much, since the index is 2, it would be nice if I can write 48 as the product of a perfect square factor and something else. In English, it would be nice if I can write 48 as something times something, where I can square root those somethings. Okay, so with your permission, we're gonna write 48 as 4 times 12. Okay, I'm gonna put 4 first, because 4 is a perfect square factor. So at this point, pretty much I use the product rule for radicals. Okay, if you have a multiplication problem, I didn't put 4 times 2 into the same roof because I'm an overachiever. Okay, we can go ahead and split it. Okay, we can write it as nth root of the first factor times nth root of the second factor. Okay, so 4 times 12 gives us back that 48 that we're square rooting. And then we're just going to square root what we can, in this case, namely the 4. Okay, so square root of 4 gives us 2. And then I want to know, well, is square root of 12 simplified? I'm like, I don't know. Does it have a perfect square factor? In semi-English, is there a nice way to write it where we can square root one of those factors? And in this case, yeah, we could still break it down, because 12 still has a perfect square factor, namely 4 again. Okay, so we're going to write square root of 12 as square root of 4 times square root of 3. So again, we're using the product rule to split the factors. So square root what we can. Okay, so we have 2 times the square root of 4, but the square root of 4 gives us 2. Product of the integer factors, namely 2 and itself, will give us 4. And that will leave us with 4 square root of 3. Cool. Now, someone said for those overachievers, let's go ahead and do this problem again. It's like, oh, you know what? I know that you use 4, but I'm cool like that. And I see a larger factor. I know that 16 times 3 is 48. I'm like, oh, that's cool. All right, I really didn't see that. So what I want to get at is this. The larger the perfect square factor that you use, the fewer steps that you will have. Okay, but what I tell my students, if you just begin to write like right now instead of later, it doesn't matter if it took you a couple of steps. You'll finish a lot faster instead of sitting there looking pretty to think of what the biggest number is. Okay, I've said too much. Cool. We already know what the answer is. Let's pretend like we're shocked after we finish simplifying. Square root of 16 gives us 4, and then the square root of 3 does not have a perfect square factor, so it will stay as square root of 3. What? We want to do this one more time? Cool. I thought you never asked. Okay, so bear in mind, if the numbers come to you, more power to you. But now the question is, what if the numbers don't come to you? Okay, if the numbers don't come to you, then I need you to write 48 as a product of prime factors. So let's go ahead, branch it out. Okay, 48, something times something, whatever comes to your mind. Our factor trees may look different, but you know what? It's okay. All our tips will match. Sorry, I'm like speed racing here. Okay, why? Because I know you can do this on your own. Okay, so we're going to write 48 as a product of prime factors. The question is, should we use exponents for repeated factors? You know what? That's really a personal choice. Of course, it would be faster if we just write 48 as 2 to the 4th times 3. But for the purpose of us seeing things, I don't recommend that you group them. Okay? So we're going to just write it out. 2 times 2 times 2 times 2 times 3. Hopefully I got them all. So we have 1, 2, 3, 4. 1, 2, 3, 4 times 3. Okay, now what if you think you messed up on the multiplication? Then punch it in and put 2 times 2 times 2 times 2 times 3, and then you'll confirm that you get 48. Now at this point, I'm going to highlight the index, okay, because it's really important for me. Index is 2, okay? So when we write 48 as a product of prime factors, we're going to start making some groups. Groups of what? Groups of 2, groups of 3, groups of 4. Our groups or our group size is going to be dictated by the index. Okay, since the index is 2, then we want to make groups of 2, and everyone needs to wear the same suit. So like we got to be twins. We got a group of 2 here, we got a group of 2 here, and then we got this solo rider. Okay, why is it solo? Because it doesn't have like a match, okay, like a twin. So all these groups, we're going to house them under its own radical. How or why? Because we're going to use the product rules. At this point, it's really up to you how you want to write, but I need you to adhere to my recommendations. I know that you know that 2 times 2 is 4, so I guess you can just write square root of 4, but I'm thinking about like how am I going to fix it when the index is higher than 2. So with your permission, now I'm going to write exponents for repeated factors. So we're going to write this as square root of 2 squared, or you can put 4, but if you just get the practice with using exponents for repeated factors, it will save you a lot of headache. We got another group of 2, so we have times square root of 2 squared, and all these solo riders, they get its own radical. Okay, so we still have 4 times 4 times 3, which gives us 48. So now at this point, I'm going to highlight the indexes once again. So then I'm like, oh, index is 2, power is 2, they're the same, so they undo each other, and that will leave you with the radicand of 2. Okay, so it's no different like if you had written 2 times 2 is 4, and then you say square root of 4 is 2. Handle it however you want, but I need you to trust me, okay? And you're watching this video, so supposedly you do, okay? Square root of 2 squared, let's go ahead, highlight that index. Okay, index is 2, and then same speech. Index is 2, power is 2, they're the same, so they undo each other. So pretty much like we're saying that the square and the square root undo each other. Okay, so that will leave us with the radicand of 2. And don't forget the operation times, and then we have times a pesky square root of 3. Let's go ahead, multiply those integer factors, and then pretend like we're surprised when we get the same answer. Product of 2 in itself is 4, and then that is being multiplied by the square root of 3. Okay, so handle it however you want. Okay, so let's go ahead, do another problem. It's gonna look very familiar, very similar, sorry. It's gonna look very similar to highlight its difference. Okay, so problem E, we're gonna say cube root of that same number, cube root of 48. Okay, sorry, blue. So we have cube root of 48. This one we'll only do twice, and the rest of the problems we'll just do once. Okay, so then when we had the square root of 48, I'm like, oh, it would be nice if I can think of a perfect square factor. Okay, first time around we thought of 4, second time around we thought of 16. Now that the index is 3, I don't have a lot of practice with those, but now that the index is 3, I'm like, it would be nice if I can think of a perfect cube factor. I'm gonna go ahead and cheat. Okay, I think a perfect cube factor is 8. So we're gonna write this as cube root of 8 times cube root of 6. Okay, before we proceed, I gotta make sure if I wrote it correctly. 8 times 6 is 48. So yeah, cool. So we just rewrote, we just used the product rule for radicals to rewrite cube root of 48. Now, if by some miracle you know what the cube root of 8 is, then go ahead and evaluate it. Okay, cube root of 8 is 2, and then we bring down the rest of the problem. 6 does not contain a perfect cube factor, so that's the answer. In all honesty, I don't think I could do it like this. When the index is 2, maybe I'm a little bit brave and I can start like to think of perfect square factors, but that's because I have practice with square roots. I don't have lots of practice with cube roots, fourth roots, fifth roots, etc. So I will typically go the prime factor route if the index is more than 2. Okay, so let's go ahead and do this again. So we have E2, we have cube root of 48. So what are we going to do? We're just going to write 48 as a product of prime factors. Let's take our work from above, and we have, what was it? 2 to the 4th times 3. Okay, 2 to the 4th times 3, but without the exponents. 1, 2, 3, 4, and then times 3. Fantastic. Okay, so now what are we going to do? We're going to start making our groups, and everyone needs to wear the same suit. Because the index is 3, we want to make groups of 3. Okay, so we have 1, 2, 3, and everyone needs to wear the same suit. We don't have enough 2s to make another group of 3. We don't have enough 3s to make a group of 3. So we're going to have 2 solo writers, and all those people, we make them mingle. So we have them under the same radical, the same roof. So let's go ahead and use the product rule for radicals to split the factors. So each group has its own like cabana per se. So we have 2 to the 3rd. The question is, can we just evaluate 2 times 2 times 2 to make 8? Yeah, but check it out. I want to ask you this. What would you rather see? Would you rather see cube root of 8 or cube root of 2 cubed? I can't read your mind, but I can tell you my speech. I will go with the second one because I'm like, look, index and exponent are the same, so they undo each other. I don't have to like visualize anything. I can see it. Okay, so index and exponent are the same, so they undo each other, and that will leave us with the radicand of 2. And I think I skipped a step because I was a little bit excited. Usually I bring down the rest of the problem and then begin to evaluate. My apologies. Okay, so we're gonna go ahead and multiply that by the cube root of these solo writers. 2 times 3 will give us 6. Okay, so that's gonna give us 2 times the cube root of 6. Now, when you write the number as a product of prime factors, it's so much easier to see if that number is simplified. We couldn't make a group of 3, so when we take their product with confidence, we'll know that in this case the cube root of 6 is simplified. Fantastic. So let's go ahead and do another problem. Where am I? Let's go ahead and do problem F. Okay. So problem F, we have square root of 200. Cool. So you have 2 ways to go about it. So we're not going to do all these problems twice because then we will never finish. Okay. So problem F, if the numbers come to you in this case, because the index is 2, if you can think of a perfect square factor, then take it. And if you cannot think of a perfect square factor, then just do what we did, prime factor it. But I can read your mind, and I know that you know that 100 times 2 will give us 200, and 100 is a perfect square factor. So let's use the quotient rule for radicals to split this. We're going to rewrite 200 as 100 times 2, or square root of 100 times square root of 2. We square root what we can, namely the 100, and square root of 100 is 10, and then we're going to multiply that by the square root of 2. Fantastic. Okay, so let's go ahead and do another problem. Remember, today we're doing lots of problems in an effort to say whatever I'm trying to say. Sorry, I'm a loss for words. I'm trying to speak to you. I'm trying to write, and then I'm putting my head to the side. Okay. Remind me not to do that. Next time I'll just pause the video. Okay, so problem G, we have the square root of 18 times x to the 6th, y to the 5th, z to the 7th. Okay, so you can handle this however you like. I'm going to do this problem twice. I'm not necessarily going to do two different techniques, but one way is just by like breaking everything down, and then another way is by doing the same thing but not writing it out. Okay, so let's do this. So the variables scare me, so I'm going to focus on the integer factor. Okay, so we have square root of 18. It would be nice if I can think of a perfect square factor, and in the event that we don't, then we go the prime factor route. But when we keep our cool, a perfect square factor of 18 is 9, so let's do that. So we're going to write this as square root of 9 times square root of 2, and all those variables will attach them to the 2, okay, to the number that we can't square root. So we have x to the 6th, y to the 5th, z to the 7th. Okay, so let's do this. When we take our time, the square root of 9 gives us 3, and that is being multiplied by the square root of 2 times x to the 6th, y to the 5th, z to the 7th. Now, the question is this radical simplified? I don't know, maybe. So let me highlight the index. We know that we cannot simplify the square root of 2, but what about these variable factors? If we have exponents inside, they need to be less than the index, and all of these are more than the index, so we can tone it down. So let's go ahead and square root these one at a time. The first one is a square root of x to the 6th. So pretty much we're gonna write this in exponential form, but I'm gonna do that in a thinking area. Okay. So square root of x to the 6th. So let's put it in exponential form or get it out of the radical. So to do that, we're going to keep the base and then write the exponent as a fraction, which will be 6 over 2. Why 2? Because we have said square root. Remember, if the number is not written, then it's implied that the index or root is 2. And then that will give us x to the 3rd power. Okay. Notice how we don't have a remainder, so that means that all the factors came out to play. So we have 3 times the square root of 2 and the square root of x to the 6th, thanks to your hard work, simplified to x cubed. Okay, fantastic. So now square root of y to the 5th. Okay, so let me go ahead and do that on the side. So we have square root of y to the 5th. So pretty much, let's go ahead and write this in exponential form, or in short, pretty much what's going on, we want to know how many times is 2 going to 5. Okay, I know you can do that in your head, but this is day 1, so I'm trying to show all my steps. Okay, so when we write this in exponential form, we have y raised to the 5/2, and then we want to highlight the quotient and remainder. 2 goes into 5 at most 2 times with the remainder 1. So what is going on? Since the quotient is 2, that means that 2 factors of y are going to come outside. Because the remainder is 1, that means that 1 factor of y will stay inside. So let's transpose that to our solution. 2 y's come out, 1 y stays in. Okay, cool. For the grand finale, square root of z to the 7th. So let me go ahead and write out my put it in my thinking area, and then we'll write it in exponential form. Okay, so that will give us z raised to the 7/2. Okay, why? Because remember, current exponent divided by the index, Quotient is not going to give us an integer, so we want to highlight the quotient and remainder. So 2 goes into 7, I think at most 3 times with the remainder 1. Since the quotient is 3, that means that 3 factors of z come outside. Since the remainder is 1, that means that 1 factor of z will stay inside. So again, let's bring that to our problem. We got 3 z's on the out and 1 z in the inside. Cool. So that's our answer. It just looks a little bit weird because we're so used to seeing the integer factor first followed by the variable factors. So we have a 3, and the order of the variable factors, it's up to you. If you're like, they must be in order to make the book happy, sure. But for me, it doesn't really matter. But if you're not going to sleep tonight, then go ahead and put them in order. I just need to see a 3, a z, a y, and an x in the order if you're liking, preferably with the 3 at front. And that is being multiplied by the square root of 2yz. Cool. That's it. Now, we're not going to redo this problem because I think what I wanted to show you, I'll do it with problem H. Okay, so problem H, where am I? We have cube root of 32 times x to the 8th times y squared times z to the 9th. Okay, so first I'm going to focus my energy on the cube root of 32, and then we'll worry about the variable factors. Cube root of 32. If I was able to think of a perfect cube factor, that would make my life so much easier. But since I generally can't, I'm going to write 32 as a product of prime factors. Okay, so when we branch out 32, I'm going to go ahead copy someone. That's 8 and 4. I'm going to just do 3 factors of 2. Typically, we just write 2 branches at a time, but I felt like being an overachiever. Okay, so I put out 3. So the moral of the story is that 32 is the same as 2 to the 1, 2, 3, 4, 5 to the 5th power. You can use the exponents if you like, and then just do the same spin that we did for the variables. But with your permission, I'm just going to write it without the exponents. 1, 2, 3, 4, 5. And then we'll tag along the variable factors. Okay. So again, I'm going to focus my energy on simplifying the cube root of 32, and then we'll attack the variable factors. So the index is 3, so we're going to make our groups of 3, and everyone needs to wear the same suit. So we have 1, 2, 3. I was going to count to 4, and then oh no, that's it. We can't make another group of 3, so those are going to be those solo riders. Okay, so we have cube root of the first group. Now we'll use exponents for repeated factors, namely 2 to the 3rd times cube root of, we know that we cannot simplify 2 times 2, so let's go ahead and give that product, namely 4, and then we'll tag along those variable factors. Okay, fantastic. We got this, guys. Okay, bear with me. Okay, so let's do this. Cube root of 2 cubed, the 3's cancel out, and that will leave us with the radicand of 2. If you want to hear my lovely voice, the speech is index is 3, power is 3, so they undo each other, and that will leave us with the radicand of 2. Okay, let's bring down the rest of this problem. Times cube root of 4, which we have established that we cannot simplify, but now it's showtime. Let's simplify those variables. Cube root of x to the 8th. What this boils down to is this. When we put it in exponential form, we will write this as x raised to the 8 over 3. Why don't we just do 8 over 3 on the side? Okay, well, with the into symbol. What this boils down to is this. I want to know how many times does 3 go into 8. 3 goes into 8 at most 2 times, with the remainder 2, I think. Okay, 3 goes into 8 at most 2 times, with the remainder 2. So since the quotient is 2, that means that 2 factors are going to come out. Since the remainder is 2, that means that 2 factors are going to stay in. And if you don't like this, then I don't like this, okay? But if you don't like this, then just do what we did earlier. Write it in exponential form and then take it from there, okay? So let me go ahead and put a little dot just to remind myself that I already took care of it. Next factor, cube root of x squared. So I'm like, how many times does 3 go into 2? I'm like, it doesn't. Okay, so we don't have enough y's to be simplified, so stay inside the radical. cube root of z to the 9th. What this boils down to is how many times does 3 go into 9? Okay, how many times does 3 go into 9? And the reason why I say that question is because if we were to put it in exponential form, it will be z raised to the 9 over 3. Here's our 9 over 3. Okay, so 3 goes into 9 exactly 3 times without a remainder. So that means that all 3 factors of z are going to come outside. So that is our answer. Let's just rewrite it to make it aesthetically pleasing. So that will give us 2 times the variable factors in the order of your liking. Okay, if you want to put the x first, go for it. Okay, it doesn't really matter. Okay, and that will give us 2 times e cubed times x squared times the cube root of 4x squared y squared. Cool. Alright, so let me go ahead and take a pause because I'm going to see if we're going to do more or that's it. Okay guys, so the people have voted and they said no más. Okay, so no more, but we're gonna do 2 more instead of my original 10 more. So we'll do 2 more and then we'll finally be out. Okay, so the directions are the same. I just put simplify the expression for my peace of mind. But again, the disclaimer: assume all variables represent positive real numbers, and then spit your answer in radical form if possible. Okay, so problem I, we have the negative 4th root of what you can read 168 to the 25th times b to the 7th. So now, it would be nice if I can think of a factor of 160 that's a power of 4, but it's just not gonna happen for me. I sincerely can't. Okay, so what am I gonna do? I'm gonna write 160 as a product of prime factors and then make my groups of 4. So let's do this. So 160 ends in 0, so I know that 10 is a factor, so I'll do 10 times 16. We branch out 10, that's 2 times 5. We branch out 4, that's 4 times 4. We branch out 4, 2 times 2, and then we do the encore presentation for another 2 times 2. So we have 160 the same as a bunch of 2's times 5, but I want to say that correctly. Okay, so we have 160 the same as 1, 2, 3, 4, 5. We have 5 factors of 2, which is 2 to the 5th power. You're more than welcome to use exponents for the repeated factors and then handle it like you do with the variables. But for me, I love making groups, so with your permission, we're not going to use exponents. So we have 5 factors of 2, 1, 2, 3, 4, 5, and then multiplied by that factor of 5, and then we have those variable factors. So a, b, fantastic. Okay, so the index is 4, so we want to make our groups of 4. Okay, so if you want to be in this group, you gotta wear the same suit. So we have 1, 2, where am I? 3, 4. Sometimes I don't know how to count. We got a single 2 and a single 5. So all those single people, we need to make a mingle. Okay, I'm not trying to be funny. That's just how I speak. Okay, so if you're in a group, you get your own cabana, you get your own radical, and these single people, they need to start talking. So we'll put them together in another radical. So that will give us negative 4th root of, now let's go ahead use exponents for repeated factors. Okay, so that will give us 2 to the 4th power. Why do I use the exponents? Well, because I rather evaluate 4th root of 2 to the 4th than 4th root of 16. So it's a personal choice. Okay, times 4th root of everything that's left. 2 times 5, with confidence we will know that the 4th root of 10 is simplified. And let's bring down those variable factors. Yeah, I need to write evenly, sorry. Okay, so let's do this. 4th root of 2 to the 4th, index is 4, power is 4. They're the same, so they undo each other, and that will leave you with the radicand of 2. Don't forget to bring down the negative sign because we're looking for the negative root. Okay, times the 4th root of the first factor, so that's just 10, times the 4th root of a to the 25th power. So pretty much we want to know how many times does 4 go into 25. And if you're like, no, I don't want to do it like that, I want to put it in exponential form, then go for it. Okay, you do what you gotta do. It's really a personal choice. So this is my thinking area. This looks like a radical, but it's a division sign. 4th root of a to the 25th, again, what that boils down to is how many times does 4 go into 25. 4 goes into 25 at most 6 times with the remainder of 1. Again, we need to highlight the quotient and remainder. If you write it in decimal form, then this is not going to help. Since the quotient is 6, that means that 6 factors of a are going to come outside. So let's go ahead put 6 factors of a on the outside. Since the remainder is 1, that means that one factor of a is going to stay in. Cool. Now, 4th root of b to the 7th, what this boils down to is how many times does 4 go into 7? 4 goes into a 7 a bunch of times. I got to write it out because I'm tired. 4 goes into 7 at most once with the remainder 3. Again, you could put it in exponential form. Since the quotient is 1, or since 4 goes into 7 at most once, that means that one factor of b is going to come outside. Since the remainder is 3, that means that 3 factors of b are going to stay inside. So that's our answer. Technically, we can't simplify it further, but let's just make this aesthetically pleasing, meaning let's put the integer factor first. So we're going to write -2, and then the variable factors, you put them in any order of your liking. Of course, if you check your answer in the back of the book, you're going to see the a to the 6th and then the b. It's really up to you. Okay, guys, so we were going to do 2 more. This is the first one. We have 1 more, and then we're out. Problem J. So problem J, we have square root 5, times cube root of 4. Square root of 5 times cube root of 4. This is a really tricky problem for me because for me, I'm really tempted to multiply the 5 and 4, you know. But remember, the product rule for radicals, so we have nth root of a times b. We can split the factors, okay? Nth root of the first factor times nth root of the second factor. If we have product of radicals, we can backtrack to a single radical only if the indexes are the same. Square root of 5. If we have the square root of 5, then that means that the index is 2. So unfortunately for this problem, we cannot apply the product rule for radicals in reverse. Why not? Because the indexes are not the same. And then I'm like, man, what am I supposed to do? The directions read simplify the expression. So again, what does it mean to simplify? That is code for clear grouping symbols and combine like terms, and if you need to multiply, so be it. I got 2 things that I need to multiply, but I can't multiply it right now. So I'm just gonna put it in exponential form. Okay, so get it out of the radical. Okay, so we're gonna keep the base of 5 and write the exponent as a fraction. So to do that, we're gonna keep the current exponent and divide it by the index. So let's get the other one in exponential form. We're going to keep the base and write the exponent as a fraction. So namely 1/3. Fantastic. So it's like, okay, where are we going with this? I don't know, but we're just going to do what we got to do. So at a first glance, I want to say, oh, look, we're multiplying 2 things. Silly exponent rules, they make me so mad. But check it out. We're not multiplying 2 things that have the same base. So even if I'm mad, I cannot use the product rule for exponents. But what am I trying to do? It would be nice if the indexes are the same. So what we're gonna do, we're gonna find the LCD for the denominators. Okay. So LCD between 2 and 3 is 6. So we want to fix it so both denominators are 6. So for the first denominator, let me go ahead zoom in. Okay, to make that 2 look like a winner, we're going to multiply top and bottom by 3. Please remember to have good notation, so don't just multiply the bottom by 3. And when we do, we will tell the world that 5 raised to the 1/2 is the same as 5 raised to the 3/6 times, okay, that 1/3 to make it look like 6, to make the bottom look like 6, we're going to give it that missing factor of 2, top and bottom by 2, and then we'll tell the world 4 to the 1/3 is the same as 4 to the 2/6. So then I'm like, okay, well, what are we doing with this? We're still not multiplying 2 things that have the same base. So that is correct. So we still can't multiply right now. But check it out. Notice how the things to our hard work, since the denominators are the same, when we backtrack to radical form, then the indexes will be the same. So let's go ahead backtrack to radical form. So bear in mind that whenever we have a rational exponent, that is code for hidden radical. So let's do this. We're going to start with the denominator. The denominator is 6, so we're going to have 6 root of whatever we're left with. 6 root of 5 to the 3rd. what's going on with that? We're going to multiply it by the 6th root of 4 squared. Cool. So now, thanks to our hard work, now that the denominators are the same, we can multiply. Okay, something that that's okay. I'm gonna say my piece later. Okay, so we have 6 root of 5 cubed times 6 root of 4 squared. Now that the index are the same, let's go ahead and use the product rule for radicals in reverse to house it under one roof. So this will give us 6 root of 5 cubed times 4 squared. Okay, so now the question is, can we simplify this? So 5 is a prime number. Okay, in this case we don't have enough 5s to come out. 4 is not a prime number, but like, let me just go ahead and write 4 squared. Okay, so 16 is the same as 2 times 2 times 2, or 2 to the 4th. Okay, in this case we don't have enough 2's to come out, so what I want to get at is that a 4 squared, what I want to get at is that the 6th root of 4 squared is already simplified, or the 6th root of 16, or the 6th root of 2 to the 4th is already simplified. Okay, so let's go ahead, simplify the radicand, and then box our answer with confidence. Where am I? 5 cubed is 125. Product of 4 squared, square of 4 is 16. Yeah, I'm a little bit nervous. So are you, I know. And then when we punch it in, the calculator gives us 2000. So 6 root of 2000. Now, we know that our answer is simplified. Why? Because we were not able to simplify the 6th root of 5 cubed or the 6th root of 4 squared. Okay, guys, that's my time. I'll watch you at the next video. Hopefully, please watch me.